The first problem here in chapter 11 is problem number 13. And this is dealing with the concept of specific heat. How much energy does it take to increase the temperature of something? So the basic equation is that the heat transfer, which is in joules, is equal to the mass times the specific heat times the change in temperature. So the more mass you have, of course, the more energy you have to put in to get a raise in temperature. And specific heat of the material is higher, then it takes more energy to raise it to a certain temperature. So, and what they're asking for in problem 13 is how much thermal energy is required. So that's the answer. So all you have to do is figure out what those numbers are. A certain steel rail yard is 13 yards in length. Okay, so let's length is equal to 13 yards. Weighs, so the weight is equal to 70 pounds per yard. So if we take length times the weight per length, really it's weight per length, 70 pounds per yard. How much thermal energy is required to increase the rail such that the length of the rail increases by 3 millimeters? So this really is a combination of two things. It's asking about increasing in length, which is chapter 10 stuff, and stopping here, for some reason my thing is not quite working yet. Okay, I think it's working again now. So this is one equation. This is how much heat transfer. What you need to figure out is delta T. And you get delta T by looking at that delta L is equal to the thermal expansion coefficient times the original length, L0, times delta T. So this is a property of the material. C is a property. Alpha is a property. We're given the length in yards. And we're given the length in millimeters, so it's probably best to convert all this stuff to metric units. So let's do that first. So 13 yards. So what I need, the conversion factor I need is meters per yard. So I go to the front of the book, I look under length, and I see that there is 1 meter equals 3.28 feet, and let's see the yards. Well, the yard is 3 feet, so we would take. So we really need two additional things here. So let me make sure I get this correct. So I'm going to move this over. So we have meters per feet or feet per meter, and then we have. So that'll give us. So we need yards, so all we need is feet per yard. See what happens, the yards cancel out, feet cancel out, again, meters. So we have 3 feet per yard, and we look at the front of the book, and we have 3.281 feet per meter, 3.281 feet per 1 meter. So this should be around like 3 or 4 meters, if I did this correctly. 13 divided by 3.281 divided by 3, or multiplied by 3, sorry, times 3. ER is close to a meter, so it actually should be around 13. 11.99. So we have 11.9 meters. So that's L. Or we can call it L or L0, something. And now we go into, we have to go back to chapter 10, find the thermal expansion coefficient for steel, which is said, chapter 10, not chapter 11. So, be looking through there so you can find it first here. Average coefficient of expansion for some materials near room temperature. So we go down to steel, and alpha is unitless because it's feet per feet. Well, actually, it's not unitless, but it just doesn't involve feet or yards. So, theoretically, we do not have to necessarily do that, but it's probably best to do it. Okay. 11 times 10 minus 6, c to minus 1. So that's the thermal expansion coefficient. And we also need the thermal conductivity, not thermal conductivity, the specific heat for steel. Then you go to page 355 for that. So steel, iron, same thing, basically. So we get 448. So make sure you know how to find this. 448 joules per kilogram degree C. Okay, before we do one more thing, let's find out what the entire mass is. So what we want is the weight per length times the length, and the weight per length is 70 pounds per yard. We multiply by 13 yards, so that gives us 70 times 13 is 910. 910 pounds. So let's go back to the front of the, we want to convert this to kilograms. And force, 1 pound, so many newtons, so we should convert to newtons. So weight is equal to 910 pounds. And we need newtons per pound. So we have, or pounds per newton. So we need newtons per pound. So the pounds cancel out and get newtons. So there are 0.2248 pounds per 1 newton. If you look under force. So we get 910 divided by 0.2248. And that gives you a weight of 4,048. We'll round up to 50 newtons. And then we can calculate the mass. The mass is equal to the weight divided by the acceleration due to gravity. So we get 4050 divided by 9.8 meters per second squared. So we divide by 9.8, and that gives us 413 kilograms. Now, a short way of doing it is there are 2.2 pounds per kilogram, so we could just take 910 kilograms divided by 2.2 pounds per kilogram. Pardon me, it's 910 pounds. 2.2, so we take 910 divided by 2.2, and we get 413. That's going to get the same number. So that's the quick way of doing it. Actually, it's 414. So we'll take this one. So that's the mass, which we're going to need here. We need that. We're going to calculate delta T. We have L0, which is this. We have alpha. Okay, so we're all set to go. So we're going to solve this one for delta T. So delta T is going to be equal to delta L divided by alpha times L0. L0 was 11.9 meters. Alpha was 11 times 10 to the minus 6. Degree C to the minus 1 power. And L0 is, L0 is in the denominator, so it's 11.9 meters. Delta L is given in the problem statement. Did I write it down? I don't think so. It's a couple of millimeters. Let's see here. Okay. Forgot what problem we're looking at. 3 millimeters. Okay, so I'm going to write this in different colors so you can see it. Delta L is 3 millimeters, which you divide by 1,000, so you get 0.003 meters. So we have 0.003 meters, which is 3 millimeters. So the units work out. Meters cancel out. It's degrees C, then minus 1 power, move the numerator, it becomes degrees C. So we get 0.003 divided by 11 e to the negative 6 power divided by 11.9. And I get 22.9 degrees C, which is reasonable. Okay, so that's good. Now that we know delta T, we can calculate the heat because we know the mass, we know that, and we know delta T. So we're going to do this. We're going to say Q, the heat transfer in joules, is mass times C times delta T. The mass was 400 and something, 413 kilograms. Specific heat was, first page, 448 joules. 448 joules per kilogram degrees C. And our temperature change is right there on the previous page. 22.9 degrees C. So you can see the C's cancel out, kilograms cancel out, and it with joules, which is what we want. So you get 413 times 448 times 22.9. You get a big number. 4 to 4 decimal point here, and if you've got a calculator, you'll count 1, 2, 3, 4, 5, 6. 6 decimals before the 4, so it's 2 times 10 to the 6 joules, and 10 to the 6 joules is a megajoule, so we'll say it's 2.42 megajoules Q. Okay, so we're going to pause just a second. Okay, I did it again. It's like Britney Spears. I forgot to push the record button, so I'll go through this again. So 13, we have a railroad rail that is 13 yards in length and weighs 70 pounds per yard. How much thermal energy is required to increase the length of such a rail by 3 millimeters? Assume the steel has the same specific heat as iron. So to find the amount of energy added through heat transfer, we use this expression relates temperature change, specific heat, and mass to that quantity. This is a property of the material. We're going to use iron. The mass we're going to have to calculate, and delta T we're going to have to calculate, because what it says is that the rail increases 3 millimeters. So we actually have to use two results. One is this, and the other one is this thermal expansion coefficient that we talked about in chapter 10. So the second equation we have is that the change in length is equal to the thermal expansion coefficient times the initial length times delta T. So what we'll do is we're given delta L, is 3 millimeters. This is a property of steel, and L0 is also given up here. I'm going to call it small l to start with, but we can call it L0. One of the key things in this problem is that you have to watch what you're doing with units. So I'm going to convert everything to SI system. So we take 13 yards, we multiply by the conversion from meters to feet and feet to yards. So what will happen is the feet will cancel out and yards will cancel out and you end up with meters. So if you go to the front of the book, there are 3.281 feet per 1 meter. And we know that there are 3 feet per yard. So when you multiply all these together, you get that the distance is 11.9 meters. A yard is a little bit shorter than a meter, so this number should be slightly less than that. So that's our initial length. We can also calculate the mass of the rail by taking the length multiplied by this weight per length, 70 pounds per yard. So if we take 13 yards times 70 pounds per yard, we can get the weight, and then once we know the weight, we can calculate the mass. So that's another thing we're going to do. From Chapter 10, this is the thermal expansion coefficient. From Chapter 11, this is the specific heat of iron. Notice these in degrees C, joules, kilograms, so this is all SI unit stuff. Okay, so let's go to the next page. So let's calculate the weight of the rail. So you take the weight per length, 70 pounds per yard, multiplied by 13 yards. Yards cancel out, and you end up with a weight of 910 pounds. So we need to, there's two ways of doing this. The first way is we're going to convert pounds to newtons because weight is a force. So we're going to convert it to the force equivalent in the SI system. So we take 910 pounds, and we need the conversion from pounds to newtons. So we need a conversion in newtons per pound. Well, the book says there are 0.2248 pounds per 1 newton. So we put this part in the denominator to get the units right. And that comes out to be 4,050 newtons. The pounds cancel out in the units. And then we can use this relationship. You know, weight is equal to mass times acceleration due to gravity, or mass is weight divided by acceleration due to gravity. So there's our weight in newtons. There's acceleration due to gravity. We get 413 kilograms. Now, a quick way of doing this, rule of thumb, is if you're at sea level, where the gravity is normal, there are 2.2 pounds per kilogram. So if you take 910, divide by 2.2, you get 414 kilograms. So basically the same thing. Okay, so we have the mass. We have that because it's a property. We're going to calculate delta T from this equation because we have the initial length, we have that, and we have delta L. So we're going to solve for delta T from the thermal expansion coefficient equation. The length, we're going to convert millimeters to meters. So you divide by 1,000. So 3 millimeters becomes 0.003 meters. Alpha, look that up in the book. L0, we do it in meters to be consistent with our increase in length. So we had 11.9 meters that we got from converting 13 feet, or 13 yards. So you get 22.9 degrees C. Plug that all in. With that delta T, then we can just go back here and plug it into this equation. So, M, we just calculated. This is in the book. This is we just calculated. So plug all this in. The units work out because the kilograms here cancel with the kilograms and the units for the specific heat. The degree C cancels out that degree C. We're left with joules. So 4.24 times 10 to the 6 joules. And we can convert that to megajoules by knowing that 10 to the 6 is a mega. So it becomes 2.24 megajoules. So that's the amount of heat transfer. And that's the right answer. And I remembered to record it this time. Okay, our next chapter 11 problem is 15. And where is it? Okay. So this is a calorimeter problem. That means that we have, typically we put something in water and we see how much it heats the water up. It allows us to measure the specific heat sometimes of the other material. Also, we could calculate the temperature increase if we know the initial temperatures of each thing. So let's just read the problem, see what it says. It's a black problem, so it's going to be reasonably easy. What mass of water at 25 degrees C must be allowed to come to thermal equilibrium with 1.85 kilogram cube of aluminum initially at 1 times 1.50 times 10 to the second degrees C. So lower the temperature of the aluminum to 65 degrees C. Assume any water turned to steam subsequently recondenses. And they're saying that because the aluminum is at 150 degrees C, which is higher than the boiling part, so there's theoretically when you drop the water in there, the aluminum will get a little bit of boiling right then, but then they're assuming that it will condense. If that happened. So in this case, we're not adding heat externally. We're saying that the system consists of the aluminum. So let me just put my little bit of aluminum here. And here's the water. And then we drop it in the water. And if we draw this kind of fake little boundary around here and define our system as such, with heat transfer and thermodynamic problems, drawing these boundaries is kind of a big deal. It allows you to make certain assumptions. So, there's no heat transfer here across this boundary. We're going to take it here, and there's going to be a transfer of energy from here to the water, but that's inside the system. So our Q is 0. Q equals 0. The external surrounding. So what we can say is that the mass of the aluminum times the specific heat of the aluminum times the change in temperature of the aluminum is, and we add that. So if we lose energy from this, we have to gain it from the other thing. So we have the mass of the water times the specific heat of water times delta T of the water. And usually what happens in these problems is we're able to figure everything out except for one thing. And typically the final temperature is the same for both objects. So the final temperature of the aluminum equals the final temperature of the water. And it's kind of like an inelastic collision. Our final velocities are the same. Well, the same thing happens here. You push it in here. And this cools off, the water warms up until you're in thermal equilibrium, and therefore there's no more heat transfer. And that's when the problem's over. And in this case, it says what mass of water. So this is our unknown. So we should be able to figure everything else out. So let's see if we can. Is the mass of aluminum given? The mass of the aluminum is 1.85 kilograms. Okay, specific heat of aluminum. Yes, we know that by looking in the book. And that's in chapter 11, beginning somewhere. Specific heat of aluminum is 900 joules per kilogram degree C. Specific heat of the water is big, 1,486 joules per kilogram degree C. Okay, so we got that. Let me just put a little mark. Yes, I had that. Yes, I had that. Yes, I had that. Okay. Delta T of the aluminum is going to be T final of the aluminum, which we're just going to call T final, minus T initial of the aluminum. And delta T of the water is the final temperature, which is the same between the two bodies, minus the initial temperature of the water. Okay, so let's see if we can find all those things. So T final is, this is lower the temperature of the aluminum to 65 degrees. So if you lower the temperature of aluminum, the water has to increase to 65 because that's where things come to equilibrium. Ti of the aluminum, 1.5 times 10 to the 2 degrees C. Why did they put it in scientific notation? Well, if they wrote 150 out, you wouldn't know if it had 2 or 3 significant figures. So by writing it out as such, we know that there are 3 significant figures. And notice that the book actually gives 3 significant figures. The temperature here, final temperature. Okay, so we need one more thing, and then we're good as gold. Whatever that means. Okay, so the initial temperature of the water. What mass of water at 25 degrees C? So T initial of the water equals 25 degrees C. So this is lower than the final temperature. This is, pardon me, this is higher than the final temperature. That's why it comes to some intermediate value depending on the ratio of the masses. So now that we know we've got everything here to solve this, we can just algebraically solve and then plug the numbers in. So let me copy this thing here over to the next page. And something went wrong there because it didn't copy. Let's just group those together. We might be able to copy it. And my paste thing's still not showing up. Okay, well, we'll just write it out. 0 mass of the aluminum, specific heat of the aluminum, T final minus T initial of the aluminum, minus mass of the water, specific heat of the water, T final minus T initial of the water. So if we solve for this, which is the mass of the water, we get this divided by that. We'll move that to the left-hand side. It'll have a negative sign, so when we divide this by negative this, we end up. So the ultimate answer is the mass of the aluminum, specific heat of the aluminum, T final minus T initial of the aluminum, divided by specific heat of water times T final minus, and this should actually be plus. This should be plus because we're adding them. The sign will work out right if we do that. So that's my fault. So it's actually going to be minus. So when that goes to the other side, it'll become minus. Or when this goes to the other side, it becomes minus, but we divide by positive things. So T initial of the water. So now we know everything. Let's stick it in there. So the mass of the water for this thing to happen is negative the mass of the aluminum, which is 1.85 kilograms, times specific heat of aluminum, which is 900 joules per kilogram degree C. T final is 65.0 minus T initial, which is 150 degrees C, divided by the specific heat of water, which is 4,186 joules per kilogram degree C. T final is 65. T initial is 25 degrees C. So this is going to be negative, which we'll cancel out with the negative there. So we get the mass of the water is 1.85 times 900 times the quantity 65 minus 150 divided by 4186 and divided by the quantity 65 minus 25. And because it's delta T, we don't have to convert them to absolute temperatures. So notice it's always the temperature difference. And then I add the negative sign. So I get positive. This is negative. This could be negative. So when I multiply by negative, I get positive. So I get 0.845, three significant figures, kilograms. Does that make sense? Well, yeah, it's kind of close to what the mass of the aluminum is. The mass of the aluminum is lower, the temperature difference is bigger, so it's hard to directly know, but it's not like 300 kilograms or 0.00 kilograms, so it looks reasonable. And I just checked the answer, and it's correct. Okay, so let's just go back and view what we did here. We drew this dashed line to represent this was the separation between the system and the surroundings. There's no heat transfer between the system, which included both the aluminum and the water and the surroundings. So we knew that the heat transfer is zero externally. All the heat transfer occurs internally. It's like the momentum is conserved when we had two things colliding. So you can almost think of this like a thermal collision. An inelastic thermal collision, or no elastic thermal collision. So this comes in, goes in the water, this cools off, the water heats up. and the energy that goes from here goes in there, and when they reach a point where they come to the same temperature, then we're in thermal equilibrium. There's nothing to drive the whole thing. It just stops at that point. And so we can use the specific heat calculations to calculate whatever is the unknown. In this case, it was the mass of water. Our next problem is 27. So now we're into the latent heat and phase change. So this is another way, when you have something that is changing phase, you can't just use the mc times delta T, because that only works when the phase is the same. So if you have a phase change, what happens is during that phase change, the temperature remains constant, but you're still putting in energy to change it from one phase to another, from solid to liquid or liquid to gas. So, and that is called the latent heat when you change phase. So if you want to find out how much energy it takes to heat something up from ice to gas, you not just got to, you don't just worry about the temperature difference. You got to think about the phase changes that occur in addition to the temperature increases. So what we have here, 27, is kind of like the last problem, except we actually have energy that can be absorbed because of the phase change. So we have a 100 gram cube of ice. So here's a little ice cube. And we drop it into a vessel, which is probably, what is it? Is it water? And the ice cube is at 0 degrees C. Oh wait, 27. Okay, 100 gram. Okay, so the temperature here initially is equal to 0 degrees. And it's dropped into 1 kilogram of water. And its initial temperature is 80 degrees. What is the final temperature of the water after the ice is melted? So it is saying that the ice melts. One possibility is that if this were cold, like 40 degrees, and you put ice in there, it may not be enough energy to as the water cools down from, say, 40 down to 32, from, say, 10 degrees C down to 0 degrees C, you may get to a point where you're down to 30 or 0, and this still hasn't melted. In this case, they say it has melted, so the final temperature of the water is going to be something above 0 degrees C. So what happens to the ice? Well, it goes through really two processes. First, it's going to melt. So then it becomes this, water. So now it's water at 30 degrees C, and if this water theoretically is still at the temperature, if this water here that's surrounding it is still at a temperature greater than 32 degrees C, then they're going to mix together, and you're going to come up with some intermediate thing. So this is kind of melt and then mix. So the question is, what is going on here? Well, again, if we draw this dashed line around this whole thing, there's no external heat transfer. So really what we have is the ice is going to melt. So we have the mass of the ice times the latent heat of fusion, which is how much energy it costs, how much energy it takes to melt. And I think we call that, what do we call that? L. Okay. So this is the mass of the ice. And then what's going to happen is you're going to have the mass of the ice still. We're going to keep it separate. We're going to call the mass of the ice, even though it's melted now, but it's still it's the liquid that was ice. Then you multiply by the specific heat of water and times delta T. And then you add the mass of the water, which is initially separated from the ice, times specific heat of water, times delta T. So this is delta T for the ice once it melts, and this is delta T for the water. Okay, so we know what mass of the ice is. We know what the mass of the water is. We know the specific heat of water. So the key thing here is we can find the latent heat of fusion of water. Delta T for the ice is going to be the final temperature, which is what we're trying to figure out, I think, minus the initial temperature of the ice, which is going to be 32 degrees C, or 0 degrees C. So this is 0 degrees C. And since it's 0, we can drop it. Delta T for the water is T final minus T initial for the water, which this is 80 degrees C. And what we're trying to figure out is, what are we trying to figure out? We're trying to figure out what T final is. Go back to the problem. This is from 27. What is the final temperature? Okay, so what we're going to do is solve for T sub F. So let's just plug everything in. So we have mass of the ice times L for water, latent heat of fusion, plus the mass of the ice times C for the C for water, because it's melted now. T final minus T initial, which is 0, plus the mass of the water times the specific heat of water times T final minus 80 degrees C. So if we multiply all this stuff out, we'll get, I'll just use M sub I for the mass of the ice, latent heat, plus the mass of the ice times C for H2O times T sub F. So that's what I get there. And then I get plus the mass of the water times specific heat of water times T sub F minus the mass of the water times specific heat of water times 80. And then we group the two terms that involve T sub F. So we'll have T sub F times the mass of the ice times the specific heat of water. So that's the first part. And then we'll have plus the mass of the water times specific heat of water. And the other term, we have plus M mass of the ice times L minus the mass of the water times specific heat of water times 80. That equals 0. So now we can move this to the right-hand side and divide by the term in the parentheses. So the algebra tells us that, well, this becomes positive and this becomes negative when we move it over. So you get the mass of the water, specific heat of the water times 80 minus the mass of the ice times the latent heat of the ice divided by the term in the parentheses, which is the mass of the ice times the specific heat of water plus the mass of the water times the specific heat of the water. Okay, so I think we know everything. We'll have to, the specific heat of water is, just use it in the previous problem, it's 4,000 something. That 4,186 joules per kilogram degree C. The latent heat of fusion of water is, let's see, 3.3 times 10 to the 5th. 3.33 times 10 to the 5th joules per kilogram. We don't have degree C because this all happens at constant temperature, so we don't have to, as long as we know it melts, we're good. mass of the water was equal to, what's the mass of the water? Let's go back to the original page. 1 kilogram. And the ice was, so this is 1 kilogram. Mass of the ice is 0.1 kilograms. Okay, what else do I need? Specific water, mass, ice. I think we have everything we need. Just need to plug them in there. So our final temperature is equal to the mass of the water. Put this in the bracket. So we have the mass of the water, which is 1 kilogram, times specific heat of water, which is 4186, times 80, minus the mass of the ice, which is 0.1 kilograms, times 3.33 times 10 to the 5th. That's joules per kilogram, divided by the mass of the ice, which is 0.1 kilograms, times the specific heat of water, which is 4186, plus the mass of the water, which is 1, times the specific heat of water, which is 4186. And hopefully this becomes a positive number in the numerator. So we get 4180. So we'll list both numbers so we can just see what they are. Hopefully that's the case. 4186 times 80 times 1 is equal to 334,880. And 0.1 times 3.33 e to the 5th is 33,330 divided by this stuff on the bottom, which is 0.1 plus 1, which is 1.1 times 4186. So we have 4,600 basically. So because this is almost 1/10 of that, you can see it's pretty close to the original. And water's not going to cool off super a lot. So plug that in your calculator and we get 65.6. So T final 65.6 degrees C. So what happens is the ice melts, warms up to 65.6, the water cools down to 65.6, and you come to the thermal equilibrium. So I'm going to stop, check the answer. Okay, I actually got 65. I'm not sure why, because I have all the same numbers. I just rounded down a little bit. Anyway, so that's the way it works. You know, if this had been 1 kilogram, then this would have been 330,000. So if you put 1 kilogram of ice at 80 and 1 kilogram of water mixed with 1 kilogram of ice at 0 degrees C, then it would come out to almost be just slightly above freezing. And if I had like 2 kilograms, then this number here would be greater than that number magnitude-wise, and you'd have a negative number, which would indicate that actually the ice does not completely melt. You'd have some mixture of ice and water at the end. Okay, so we are on problem number 30-something, 39. So we have a concrete slab, which is 12 centimeters thick. So here's our slab. It's our cross-sectional view. Here's the slab. So what we're going to do is we're having, this is like the driveway, and underneath we have these coils, which generate a certain amount of power. And this is 12 centimeters. And the area of this surface is 5 meters squared. Heating coils are installed underneath the slab to melt ice on the surface in the winter months. What minimum power must be supplied to the coils to maintain a temperature difference of 20 degrees C? So what we have is that Q dot, which is the heat transfer rate, is equal to, where is it? I forgot here. So let's go here. Make sure it's heat transfer rate. Heat transfer rate's like joules per. Okay, they call it P. Okay, so the book says P. In engineering, they use Q for heat transfer, and the dot represents represents the rate of change of the heat transfer with respect to time. So it's like Q prime on your physics, guys. Okay, so anyway, that's the power we're talking about. Because the power that's generated in the coils is converted to heat. So it's really power is converted to heat, which is not really power, it's heat transfer rate. Okay, anyway, we have K times A T hot minus T cold, or T cold, yeah, divided by L. So that's the equation that governs conduction heat transfer, or conducting to a solid surface. Well, we know A is 5 meters squared. We know L, which is the thickness, is 12 centimeters, which is 0.12 meters. We know that TH minus TL is equal to 20 degrees C. So the only thing I have to do is figure out what K is. What is this is called the heat transfer coefficient for concrete. So that's not too hard. Just look in the book. So each material has thermal conductivity. So if you go to page 367, table 11.3, see there's metals, gases, and nonmetals. Well, it's non-metal, and you see concrete. So K, which is thermal conductivity, is 1.3, and the units are joules per second meter degrees C. And that's because when we multiply by the area, it's going to be meters squared. So they'll cancel out with one of the meters. We divide by meters, so that's another meter. And then you have degrees C, and you end up with joules per second, which is power, or heat transfer rate. So all we have to really do is just plug the numbers in. So that was an easy one. 1.3 joules per second meter degrees C. That's in K. Area is 5 meters. And notice, I think it's at 5.0. So I guess we have two significant figures. 5.0 meters squared times the temperature difference, which is 20 degrees C. And again, because it's difference, we don't have to convert to Kelvin. What we have to convert to Kelvin is determining the speed of sound, which is an absolute temperature. Okay, L is 0.12 meters, 12 centimeters. So we just plug in, get our calculator out, which I have to do. Okay. So I think I left my calculator in the room. Okay, so I'm going to have to pause and go get my calculator. Okay, well, luckily it was there, so now I'm ready to do it. Okay, so we take 1.3 times 5 times 20 divided by 0.12, and I get 1080. We only really have two significant figures, so I could put 1100, but really I should put 11 times 10 to the third joules per second. And a joule per second is a watt. So that's a little over a watt, kilowatt, 1,000 watts. It's like a hair dryer, I think. So if that's right, let me pause, look at the answer. Okay, so yes, I have checked it. So that's actually amazingly small in some ways. But yeah, 1,000 watts is about a good hair dryer. Problem number 44. So let's see where we are. 44. Okay, so 44, 42. 42. So this is a house. And this is the average thermal conductivity of the walls and windows, including windows and roof of the house, is 4.8 times 10 to the minus fourth. So this is the thermal conductivity. K is 4.8 times 10 to the fourth. Well, actually, it's not K. It's K times A. Because if you look at the units, you'll see it doesn't make sense. It's K times the area. So K times A is 4.8 times 10 to the minus 4 kilowatts per meter degree C. Because if you look at thermal conductivity, the units, so we go to the page which has thermal conductivities on it. You see it's joules per second, which is a watt per meter. Oh, no, actually it isn't. So it is just K. Okay. Okay. So it's a watt is a joule per second. So let's convert it to joules per second. So a kilowatt is kilojoules. Kilojoule is 1,000. So you multiply this by 10 to the third, and that would give you 4.8 times 10 to the minus 1 joules per second meter degree C. Joule per second is a watt. To get kilowatts, you divide by 1,000. Anyway, they put it in kilowatts, so I think that the answer is in kilowatts, so we don't have to. We'll still use this one, but and their average thickness L is 21 centimeters. What is 21 centimeters? Well, 21 divided by 2.54 inches per centimeter. Centimeters per inch, you get about 8-inch thickness, which is actually pretty thick. Okay, the house is heated with natural gas with the heat of combustion of 9,300 kilocalories per meter cubed. How many cubic meters of gas must be burned each day to maintain an inside temperature of 25 degrees C if the outside temperature is 0 degrees C? Disregard radiation energy loss by heat through the ground. So what we have is the heat transfer rate, which they call the power, is equal to K times A times delta T all over L. So we have the thermal conductivity. We have delta T, which is 25 degrees C. We have L, which is 0.21 meters. So the only thing we don't know is area, so we can calculate area. And then what we're going to do is, it says how many cubic meters must be burned each day. So we're going to figure out how many seconds are in a day. That'll allow us to calculate the total heat transfer, not the heat transfer rate. If you take heat transfer rate and its constant times the time, that gives you heat transfer. So this is going to be joules per second times seconds gives you joules. So that's energy. And then we have kilocalories per meter cubed. So we're going to have to convert that to joules. There's a conversion factor for that. So that's the basic idea. We're going to calculate the area just from the geometry. We'll calculate this, solve for Q by multiplying by 24 hours in terms of, and it'll be seconds, because we'll have, so we'll get number of seconds in the day. That'll give us this, and then that also has to be balanced by the amount of heat that's added through the furnace. Otherwise it would get colder. Okay, so here we go. What is the area? Well, what we have is if you look at the figure, you should draw it. It's kind of like a box with a top that's not really a box. So we have the gable ends. We have the roof. Okay, so we have two of these. We have two of those, one for the front and the back, one for those. We have two of those, and we have two of those. The roof, front, back, the gables, two ends. So we just have to figure out what each one of these is and then multiply it by 2. So this area right here, we'll just draw a line over. This area is just 8 times 5. Because this is 8 and that's 5. So those are meters, so we get 40 meters squared. And we'll multiply that by 2 in the long run. Okay, let's do this one. This is another easy one. That is 10 by 5. So the area, let's call this 1, 2, 3, 4. So A1 is this, A2 is 10 times 5. And we get 50.0 meters squared. Okay, that part there, well, it's going to be this distance times that distance. So this distance is 10 meters. The other way you have to use the trigonometry because this is 37 degrees. So if we draw a triangle like that, so let me just draw this triangle. So there's the triangle. This is 37 degrees. This distance is, the total distance is 8, so this is 4. This total distance here is 8, so half of that's 4. So what we need to do is figure out the length of the hypotenuse. So this is h. Well, we can use the cosine of 37 degrees is equal to the adjacent over the hypotenuse. So h is equal to 4 divided by the cosine of 37 degrees. Make sure your calculator's set to degrees when you do this. You know, it should be somewhat bigger than 4, but not so much bigger. It's realistic. So we take 4 divided by the, let me check the mode here, which I'm in radians, so let me change that. So we get 4 divided by the cosine of 37. That's 5. Okay, that's probably why they chose it. It's a 3, 4, 5 triangle. So you've got 5 meters. So this distance is 5 meters. This distance is 10 meters. So the area of one part of the roof, so A3 is going to be 10 meters times 5 meters. So that's 50 meters squared. Okay, now finally we're going over here to this little triangle. And so basically it's going to be the height times the base divided by 2. So, you know, we could draw this over here. We could find the area of one triangle and then multiply by 2. Or we can just make a big triangle. So this length here is going to be equal to, this is the opposite, that's the adjacent. So we have the tangent of 37 degrees is equal to, what do I call that? We'll call that little l is equal to opposite over adjacent. So we can solve for L. It's equal to 4 times the tangent of 37 degrees. Just create this ratio, cross multiply. Okay, so 4 times the tangent, 37. And we get 3. So this is 3 meters. So what we have is 3, 4, 5. 3, 4, 5 triangle. Okay, so A4 is going to be equal to 1/2 the base times the height of the triangle. The base is this distance, which is 8, times the height, which is 3. And so what do we get? 8 times 3 is 24, divided by 2 is 12. 12 meters squared. So to find the total area, we add up all the individual areas, which is, and we're going to multiply by 2 because we have 2 of each. So we have 40 meters squared plus 50 meters squared. So this is just the end of the house. This is the side of the front of the house. We have the roof, which is also 50 meters. And we have the 2 end gables, which is 12. So 40 plus 50 plus 50 plus 12 divided by, or times 2 is 304. So the total area is 304 meters squared. And that's the area that we'll use in the calculation of the heat transfer. But first, so we take heat transfer rate, which is Ka delta T over L. So we just have to plug them in here. We got that the heat transfer coefficient, I'm going to write it out as 4.8 times 10 to the minus 4 kilowatts per meter degree C times the area, which is 304 meters squared times delta T, which is 25 degrees C, all divided by L, which was 21 centimeters, which is 0.21 meters. So that's the heat transfer rate. That tells us how fast the heat is leaving per second. 4.8 e to the minus 4 times the area, 304, times the temperature difference, 25, divided by 0.21. So we get Q dot is 17.4 joules. Well, it's actually kilowatts. Kilowatts, meters cancel out, degrees C cancel out, so we get kilowatts. Or 17,400 watts, which is 17,400 joules per second. Okay, now what we have is the furnace that's burning. And the furnace says, okay, we have, you get 9,300 kilocalories per meter cubed. And asks is how many cubic meters must be going. So first we need to convert this kilocalories to joules. So let's see if I can find that in there. I have to look. 1 calorie equals 4.86 joules. See if there's anything else. 254 calories equals 1.054 to the third joules. Okay, so we take 9,300 kilocalories per meter cubed, and if we multiply by 1,000, that'll get us into calories. So there's 1,000 calories per kilocalorie. Okay, now what we need is a conversion from calories to joules. So we have 1 calorie is 4.186 joules. So let's multiply that out. 9,300 times 1,000 times 4.186. So that is 3.9 times 2, 3, 4, 5, 7 numbers after the decimal point. 10 to the 7th joules per meter cubed. So what we're trying to do here is figure out how many meters cubed. Okay, so what we're going to do is we are going to convert this. So let's go back over here. The total amount of heat is Q dot times the time. So Q dot, that was the heat transfer rate, 17,400 joules per second times seconds per minute. And if you look at time on the conversion, 1 day is equal to 8.64 times 10 to the 4th seconds per day. So 17,400 times 8.64 e to the 4th. I get, so the total amount of heat that goes out of the house is 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9th joules. So here I've got joules per meter cubed. Here I've got joules. So if I take this number and divide by that number, I should end up with meters cubed. So the answer meters cubed of gas is going to be equal to 1.5 times 10 to the 9th joules divided by 3.9 times 10 to the 7th joules per meter cubed. And when I divide it, this meters cubed will come up the top, and I'll get just meters cubed. So I have that number divided by 3.9 e to the 7th, and I end up with 39 meters cubed of gas. Okay, that's problem number 42. So let's pause and check the answer. Okay, I got it right. So let's kind of review what we did. Okay, we were given this average heat transfer coefficient for the different kinds of insulation, windows, etc. in the house. We had this was the thickness of the insulation. So we use this result. The heat transfer rate, or the power, is equal to the heat transfer coefficient times the area times delta T over L, which is, this is the thickness. So we knew this, we knew that, we knew that. We didn't know the area, so we drew our house, found the areas of each one of these sections. And we multiplied them by 2 because there's 2 ends, 2 fronts, 2 back, 2 sides, front and the back, 2 side parts of the roof. And when we just found the area of the rectangle, area of the rectangle, area of the rectangle, we had to find this length through the Pythagorean theorem, given one of these lengths in this angle. That was also a rectangle, and then these were triangles. And we did that, and we got a total area of 304 meters squared. So that's the total area over which the temperature difference is being seen. So once we had the area, we plugged it in here, and we got that for each second we were losing so many joules of heat. This had units of kilowatts, meters. These meters squared canceled out with that meter and that meter, and the degrees C's cancel out, so we ended up with kilowatts, which is a power, multiplied by 1,000 to get in watts. And a watt is a joule per second. And we then multiplied this heat transfer rate by the time. Time is in seconds. So for 1 day, we needed 1.5 times 10 to the 9th joules of energy that gets transferred from the hot body to the cold body. We have to make that up somehow by burning fuel. So we looked at the fuel. It gives us 9,300 kilocalories per meter cubed. We converted kilocalories to calories by multiplying by 1,000. We converted from calories to joules by using this conversion factor. And we came up with that each cubic meter can provide 3.9 times 10 to the 7th joules. So we take the total amount of energy that we need to maintain the temperature difference, 25-degree temperature difference, and we divide by this joules per meter cubed, because that results in giving us the number of meters cubed. If I take 39 times this, then I get that number. That's what I need. Okay, problem number 44. A thermocline window consists of 2 glass panes, each 0.5 centimeters thick, with a 1 centimeter thick sealed layer of air in between. The inside surface temperature is 23 degrees C, and the outside surface temperature is 0 degrees C. Determine the rate of energy transfer through 1 meter squared of the window. Compare your answer with the rate of heat transfer through a 1 meter squared of single 1.0 centimeter thick pane of glass. Okay, so we're talking about heat transfer rate. That's equal to K times A times delta T divided by L. Now, what we're going to do here is Now this works good for just a single item. But if you got more than one item, then we have to deal with it slightly differently. And so we're going to go back and look to see what we have available. So we're actually going to use an R value. So the other way of writing this is it's A delta T over R. The R value is K over L. It turns out that if you add the R values together, you get a total R value. So rather than, if you have separate items and they're kind of together, it's a little more complicated to do it that way, because you can't just add the heat transfer coefficients. It turns out that the heat transfer rate has to be the same through each element. So the temperature difference across each thing, each part of the sandwich is different, and so it's more like I said, more complicated. So let's write down what we have. We're going to go to page 369 to get all this information we need to finish the problem. But we have 2 panes of glass each. Okay, so we have glass, and it's 0.5 centimeters thick. So that's one layer. Then we have 1 centimeter air, 1.0 centimeters. And then we have another pane of glass, 0.50 centimeters thick again. And the R value is based on a certain thickness, and if you have half the thickness, then you have half the R value. So if we look in the chart, if we look at our chart for these particular items, we see, let's see, where we have glass, flat glass, 125 inches thick. So how many, to get half an inch, we have to have 4 of that amount. So we're going to take 0.89 times 4. This number comes from table 11.4. So that'll be our answer for the R value. So we're going to do the R values. Air, stagnant layer of air, or vertical airspace, 3.5 inches thick. And, oh, these are not, yeah, it's not centimeters. I always mess that up. Okay, so let's add another page, a little more complicated. So, and these are in feet squared, degree Fahrenheit, hours per BTU. So it's going to kind of have this mixture of things. So let me just hold on just a second. Okay, so what I was doing was just checking something. So they actually, I thought it was kind of weird that they were using different units. So what they do is we still sum the R values together, but we calculate the R values for each one of these, and R is equal to L over K. So we're going to actually calculate the R values. So the R values for glass is going to be L, which is the thickness. So we have 0.005 meters divided by, that's 0.5 centimeters, divided by the thermal conductivity of glass, which is 0.84. And the units are joules per second meter degree C. So we get 0.005 divided by 0.84. So that's 0.00595. And the units will be make sure we get this right here. Meter squared degree C second per joule. If you look at table 11.4, you can see for the English units, the U.S. customary, you have feet squared, degree Fahrenheit, hour per BTU. So I've got area, temperature, time, and energy. So that works out. So that's for the glass. We have that twice. And then we have for the air. So the thickness of the air is 1 centimeter, which is 0.01 meters. The thermal conductivity for air is 0.0234 joules per second meter degree C. So 0.01 divided by 0.0234 is equal to 0.427 meters squared degree C seconds per joule. Notice the air has a pretty high R value. Higher R value is better for insulating. So we get a lot of insulating value out of the air. That's why we have thermal pane windows, double pane windows. Okay. Now that we have those, we can say the total R value is going to be equal to 0.00595 times 2 plus 0.427 times 1, 0.0595 times 2 plus 0.427, and I get R is equal to 0.546, and the units are meter squared degree C second per joule. Okay, again, the heat transfer rate is A times delta T over R. So in this particular problem, it said find the energy. So the area is 1 meter cubed because they say find through 1 meter over 1 meter squared, and delta T is 23, and so it's 23. So delta T equals 23 degrees C. Okay, determine the rate of energy transfer. So all we have to do now is just plug in the rate of energy transfer is equal to 1 meter squared times delta T, which is 23 degrees C, divided by 0.546 meters squared degree C seconds per joule. You see the meter squareds cancel out. Those cancel out, and the joule comes up front, so we get joules per second. And did they say what units? Find the energy transfer, the rate of energy transfer. Okay, so 23 divided by 0.546. 23 divided by 0.546 is equal to 42. 42.1 joules per second, which is 42.1 watts. Okay, let me just make sure that's right before we go to the next part. Okay, I messed up there. Calculator error. So I multiplied by 0.05 instead of 0.005. So what you get is 0.44. So the heat transfer rate, that should be 0.44. So we take 23 divided by 0.44. We get 52 joules per second, which is 52 watts. Now, if we only had a single pane, we just have the R value. We'll call it R single pane would be 0.00595 meters squared degree C second per joule. And so if we plug into here, we'll have 1 meter squared times 23 degrees C divided by 0.00595 meters squared degrees C second per joule. And it's a much larger value. 1 times 23 divided by 0.00595 and I get 3,860 joules per second, or 3.8, or yeah, so it's a huge difference. Make sure that's right. Just check the answer again. So 1.9 kilowatts. They said 1.9 kilowatts. Okay, what did I do wrong here? Oh, they said if it's twice this thickness. Instead of having two thinner panes, you just have one thicker pane. So it would actually be half of that. So this number we'd actually do this times 2, this times 2, which makes just divided by 2, which gives us 1,900 joules per second, or 1.9 kilojoules per second, or kilowatts. So this is 35 times that. So it's huge, huge, huge. 46. So we have a styrofoam box with a surface area of 0.8 meters. So let's write that down. This is 46. So our surface area is 0.80 meters squared. Wall thickness of 2 centimeters, which if we divide by 100, get 0.2 meters. Temperature of the inner surface is 5 degrees. So TL 5 degrees C, and the outside temperature, TH, at 25 degrees C. So our delta T is equal to 20 degrees C. If it takes 8 hours for 5 kilograms of ice to melt in the container, determine the thermal conductivity of styrofoam. So our heat transfer rate is K/A delta T over L. So we're asked to calculate thermal conductivity. So we need to know area, which we do know. We need to know delta T, which we know. We need to know L, which we know. We need to know Q dot. Okay, so that's the only one we might not know. But if we figure out how much energy it takes to melt the ice, that's just going to be m, the mass, times the latent heat of fusion of water. That'll give us Q. And then if we take that Q that we get from here and divide by T, we get Q dot. So that's how we get the Q dot, and we solve for K. Okay, so what are we going to do first? We're going to calculate Q. So the heat required to melt the ice is going to be equal to the mass, 5 kilograms, times the latent heat of fusion of ice. So we have to go to page, put that table for water. For water, latent heat of fusion is 3.33 times 10 to the 5th joules per kilogram. So that's, I'll check my calculator on, 5 times 3.333, so we get 16.6 times 10 to the 5th joules. The heat transfer rate to get that is going to be, you take Q and divide by T. It's going to be joules seconds, so you get joules per second. So we're going to have to convert the time to seconds, which is not that big a deal. So we take the Q and, how long did we say, 8 hours? I think it was 8 hours. So you have 8 hours times 60 minutes per hour times 60 seconds per minute. These cancel out. Let's cancel out. We'll get seconds. So here's 16.6 e to the 5th divided by 8 divided by 60 divided by 60. And so to melt 5 kilograms of ice in 8 hours, the heat transfer rate, the average heat transfer rate would have to be 57.6 joules per second, which is a watt. Okay, now we can take this expression and solve for K. So we have Q dot is equal to K times A times delta T divided by L. So K is Q dot times L divided by A divided by delta T. Q dot 57.6 joules per second. L was 0.02 meters. The area was 0.8 meters squared. And the temperature difference was, I think, 20 degrees C. 20 degrees C. So the thermal conductivity has to be 56.6 times 0.02 divided by 0.8 divided by 20, which is 0.072, and the units are going to be joules per, so this meters cancel out on those, so joules per second meter degree C. So is that the right units for K, joules per second meter degree C. Okay, so that's my answer. Let me just check the, so that was 46. 7.2 times 10 to the minus 2. 0.072. So let's see what I had. 0.072. Hey! Good. Okay, 72. Now the blue problem. An ice cube tray is filled with 75 grams of water. After the filled tray reaches an equilibrium temperature, 20 degrees C, it is placed in a freezer set at minus 8 degrees C to make ice cubes. Describe the process that occurs as energy is being removed from the water to make ice. Calculate the energy that must be removed from the water to make the ice cubes minus 8 degrees C. So the process involves, the first part is the water starts out at 20 degrees C, and then it goes to 0 degrees C, and this is liquid. Then it stays at 0 degrees C, and we have fusion as it freezes. So that's the second thing. And then the third thing is it goes to minus 8 degrees, and this is solid. So we really got three things. We have, and for the first part, the heat transfer is equal to the mass times the specific heat of liquid water times delta T. For the second case, we have the mass times the latent heat of fusion. And the third case, we have the mass times the specific heat of solid water times delta T. So if we just add all those things up, we get the amount of energy. Q is energy. Q dot is power or energy, rate of energy. So really all we have to do is let's list everything we know. We know the mass is 75 grams. So we'll convert that to kilograms by dividing by 1,000. So we get 0.075 kilograms. Specific heat for liquid water, 4,186 joules per kilogram degree C. Today we were looking at those numbers, and the specific heat for liquid water was like 2,000 something. Find it. I guess it's right in the beginning here. Okay, page 355, table 11.1. Water, liquid, ice, area ice, 2090. So the Specific heat for solid is 2090 joules per kilogram degree C. The latent heat of fusion is, we just used that in the previous problem, 3.33. 3.33 times 10 to the 5th joules per kilogram. And the delta T is 20 degrees, so delta T equals 20 degrees. There's no temperature change. Others, for the solid part, the temperature change is 8 degrees. And I guess this should be negative because we're taking energy out. So all we have left now is just to add all this stuff. So the total heat removed is the mass times the specific heat of liquid times delta T of the liquid part plus the mass times the latent heat of fusion plus mass times the specific heat of the solid times delta T of the solid. So 0.075 kilograms times 4186 joules per kilogram degree C times delta T, which is negative 20 degrees C. So that's that part. 0.075 kilograms times 3.33 times 10 to the 5th joules per kilogram. And then the final one is 0.075 kilograms times 2090 joules per kilogram degree C times negative, and this is going to be negative as well because we're taking energy out, negative 8. So just plug that in the calculator and get the answers. 0.075 times 4186 times negative 20 minus 0.075 times 3.33 e to the 5th power minus 0.075, actually plus 0.075 times 2090 times minus 8. And I get Q is equal to negative 30,000. Exactly. Wow, that's wild. Okay. Joules. Okay, let me just check the answer for number 72. Okay. So they got 32.6 kilo, 32,000. What did I get? 30,000. Make sure I answered the problem correctly. -20 degrees, negative 8, 0.075. Sure. Let me just pause because I don't really see what we'd do differently. Okay, it was just I plugged the calculator number wrong. I don't know what it's wrong, but anyway, it's 32,500. That would be negative 32.5 kilojoules. Divide that by 1,000, you get that.